We hear all the time about how medical AI is going to revolutionize diagnostics, right? But what if the biggest thing holding it back isn't the algorithms, but the data itself? Today, we're diving into something called the Pathology Atlas. It's a project with a really audacious goal: to solve medicine's data crisis by creating an infinite supply of artificial data, all to help save real lives.
So before we can really get into the solution, we have to wrap our heads around the problem it's trying to solve. For all the talk about complex algorithms and supercomputers, the biggest roadblock for medical AI has been something way more fundamental, something that's been hiding in plain sight this whole time.
So what is it? What's the one thing that's really holding back the development of these smarter, faster diagnostic tools? Well, it's not a lack of computing power, and it's not a lack of brilliant engineers. Nope, it all boils down to the data.
The real issue here is a critical shortage of high-quality pathology slides. We're talking about those microscopic images of tissue that are, quite literally, the bedrock of diagnosing diseases. Think about it this way. AI models are kind of like medical students. To become experts, they need to study thousands upon thousands of examples. But right now, the library is almost empty.
But why is this data so hard to get? It's not just that it's rare, it's that it's inaccessible. The data is effectively trapped. It's either locked up behind super expensive academic paywalls, or it's buried deep inside clunky hospital IT systems. And for a lot of rare diseases, it just plain doesn't exist in the huge quantities that you need to train a really good AI.
And this is the part that really matters. This isn't just some academic problem or a technical headache. This data bottleneck has serious, real-world consequences. It means researchers can't build better tools, diagnostics take way longer than they should, and the human cost, well, it's immeasurable. The stakes just couldn't be any higher.
But, a problem of this size also creates an opportunity for a truly groundbreaking solution. And that brings us right to the heart of this explainer, the Pathology Atlas.
Okay, so the core idea behind the Pathology Atlas is synthetic data. So what on earth does that mean? Well, it means using AI to generate brand new, incredibly realistic images of human tissue. These aren't copies of real patient samples, they're entirely new creations, engineered to be so accurate and so detailed that they can be used to train medical AIs, researchers, and even students.
And that's pretty much the mission in a nutshell: to build a gigantic, open-source library of these synthetic slides. It's all about taking a resource that was once super scarce and making it abundant and accessible to anybody, anywhere on the planet, completely free of charge.
But the ambition here doesn't just stop at creating a digital library. Oh no. This project has a much bigger vision for the future. A three-phase plan that's designed to turn this resource into a powerful engine for medical innovation.
So here's how it's going to unfold. Phase 1 is the foundation, and it's already live right now, a public website where anyone can just go and browse these synthetic images. Phase 2 is where it becomes a real tool for builders, an open API. That's basically a direct pipeline that lets developers access the data programmatically, getting rid of all the usual legal and licensing headaches. And then there's Phase 3. That's the dream. Imagine an AI team needs a huge data set of a very specific, very rare type of cancer cell. This system could just generate it for them, right on demand.
So you might be asking yourself, why go to all this trouble to create artificial data? Why not just stick with using real patient data? And that's a fair question. The answer, though, lies in the fundamental problems with real-world data.
The case for going synthetic becomes crystal clear when you put them side by side. Real-world patient data is just a logistical nightmare. It's tangled up in privacy regulations, it's expensive to get, and a lot of the time it just isn't available in big enough batches. Synthetic data completely flips that paradigm on its head. It's built to be open, it can be scaled up infinitely, and, this is the big one, since it never came from a real person, it sidesteps all those privacy concerns from the get-go.
And if this sounds like something out of science fiction, I promise you it's not. This whole concept is already battle-tested in other industries. Self-driving cars learn how to handle dangerous, weird situations by training in simulated environments. AI models learn to analyze satellite images by studying synthetic landscapes. Applying this same proven tech to pathology, well, it's not a leap of faith. It's just the next logical step. Of course, a project this ambitious can't be built in a vacuum. It absolutely requires a community of experts and supporters. And this is the point where the Pathology Atlas goes from just being a product to becoming a real collaborative movement. And this is a really important point to stress. This isn't just a theoretical idea stuck in a research paper. The Pathology Atlas is a real, functional product that is live right now. It's a living platform, and it needs collaboration from the community to actually reach its full potential.
And so this is pretty much a call to action. The project is actively looking for collaborators. Whether you're an AI researcher who's hit that data wall, an investor who wants to fund critical open source infrastructure, a pathologist with deep domain expertise, or a professor who just needs better teaching tools for your lab, there's a role for you to play here.
This quote right here, it just perfectly captures the massive scale of the ambition. Now, for anyone who doesn't know, ImageNet was this legendary open data set of images that basically lit the fuse for the entire modern AI revolution. By giving researchers this huge shared resource, it just unlocked incredible progress in computer vision. The goal here is to do the exact same thing, to create the ImageNet for pathology, that one foundational data set that could do for medicine what ImageNet did for AI.
And so that's the powerful question we're left with. If we can actually solve this data bottleneck, if we can give our brightest minds the fuel they need for their AI engines, what else becomes possible? An open source atlas like this isn't just a tool, it's a key, and it just might unlock a future of medicine that we've only just begun to imagine.